Have you ever wondered how a graphing calculator is able to graph really complicated functions? Well, in this section, we get to find out. We're going to do all the math behind that's hidden behind graphing complicated polynomials. So just a little bit of vocabulary. We have a polynomial. We want to put it in descending order, so the highest exponent comes first. That's the degree, and its coefficient is called the leading coefficient. And let's see. Oh, and then, yeah, sometimes we'll call just the plain number the constant term. So we're going to graph polynomials, and the easiest polynomials would be a monomial when there's just one single term. And so if we have a degree of 0, like x to the 0, that would be a straight line. A degree of 2, x squared, that is a parabola. And then we start getting into higher degrees. So x cubed is this line where you see as x goes towards infinity, so does the y. The y is going up and up and up. Okay, so y goes towards infinity as x goes towards infinity, right? So we'd have some point at x equals 100, and then y is 100 cubed. So they're just getting bigger and bigger, and then they get more and more negative. So we would say in this case, y goes towards negative infinity as x goes towards negative infinity. All right, and then you can see with even degrees, they're both the x and the y is going upwards as x gets smaller and also as x gets larger. Okay, but you'll see this behavior with an odd degree where it's kind of this, this curve where one side's going down while the other side's going up. All right, so just knowing that sort of general shape of those graphs, we can use transformations of monomials to graph those. So if I see a x cubed, I want this picture to go off in your head. And so then we see that it's x cubed but minus 1. So this graph would just slide down. It would still have the exact same shape. It would just slide down 1. So we would have, instead of the x-intercept being at 0, we're sliding down to 1. And then we still have this point here. If you take 1 and cube it, there's a 0.11, but that's slid down. So instead now of when x is 1, we're just subtracting 1 to the output. So that would be at negative 1. And then here at negative 1, when you cube that, you're at this point, negative 1, negative 1. So that will have also slid down. Negative 1, we subtract 1 more from the output, so we'd be down at negative 2. And then our graph has that general shape. All right, now here, the leading coefficient here is, it's like having a little negative 1. So what happens is we reflect across the x-axis. So usually our graph goes of x cubed goes like this. Okay, but now we need it to reflect across the x-axis. So it's going to come down. So instead of having a point at 1, 1, now we're going to have a point at 1, negative 1, and then this point here. Usually we would have it at negative 1, but it'll be at negative 1, positive 1. Okay, and then we also need to deal with the fact that we're sliding up 5 units. Okay, so we'll just take this whole graph and slide up 5 units. Okay, and so then we're going to add 5 to the output. So we'll have a point here at, this is at 0, 5. And then we have our new point at 1, 4. And then our new point here, we're just adding 5 to the output. So this would be at negative 1, 6. All right, and now I see this one. I'm adding 3 to the input. So what happens there is we have this original y to the 4th graph, but it's just going to slide the whole thing left. 2, 3. So originally we would have that x-intercept at 0, 0, but now it's going to be at -3, 0. And then our y-intercept, we find the y-intercept always by putting 0 in for our input. So we would have 3 to the 4th, 81. So it's pretty steep, and then it goes way up because that y-intercept needs to be up all the way to 81. And if you start really working with these, what you'll notice is as our degree gets higher, it flattens around the x-intercepts. They become more and more flat than these lower degree ones, and then it's much, much steeper everywhere else. Right, so, whoops. So end behavior for polynomials, as we get more complicated, so if we're not just dealing with a single monomial, but much more complicated functions, we're going to start needing to kind of think about how we're going to graph this. So a couple things, there's no holes or breaks, so there's no jumps like this or no little weird holes that you would get in rational equations, and there's also no corners, or these are called cusps, where it's like goes up to a kind of a point. Okay, so they're smooth and continuous functions. And then we were looking at this for x cubed, y equals x cubed, that idea that one side is going down while the other side's going up. And so we use this notation, y goes towards infinity, so it's positive as our x's are also positive. As x gets larger and larger, the points along here, the y's would also get larger and larger. Okay, and then here the y values are getting more and more negative as x gets negative. Now, if our leading coefficient had been negative, it would just reflect that across the x-axis. So we get this where it's just reversed. And then here we have even. So these are kind of like our, that y equals x to the 4th. But as we get more complicated with more terms, we're not sure exactly what happens in the middle. There might be a bunch of x-intercepts. There might be some local max and minimum values. Okay, but the behavior on the ends is if it's an even degree with a positive leading coefficient, both the ends are going up. And if it's a leading degree, an even leading degree with a negative positive or a negative leading coefficient, then they're both going down. So let's see, we're going to just use symbols to kind of understand and think about the end behavior. So I have a leading coefficient that's negative, and I have an even degree. So what that means is, okay, even degree. So the behavior, the ends do the same thing, but because that leading coefficient is negative, then both the ends are going to go down. And then we're not really sure what happens in the middle. There might be a bunch of other stuff, but at least we can tell what would be happening at the end of the, towards the ends of those graphs. Okay, let's look at this one. If there's no coefficient, it means there's a little 1. So we have a degree of 7 and a positive leading coefficient. And so what that means is that it's going to go, we're not sure what it does in the middle. Okay, but here, y goes towards infinity as goes towards infinity. Here we have y going towards negative infinity as x goes towards negative infinity. And here we have y going towards negative infinity as x goes towards negative infinity. And likewise, y is also going towards negative infinity as x goes towards positive infinity. X And all right, good. So now let's think about what's kind of happening in the middle. So we can always find the x-intercepts by, those are called the zeros. And so we can factor, we can also use quadratic formula, whatever we need to do to figure out the zeros. All right, so let's just start with something kind of familiar, a quadratic. So here, let's see, I can factor that. So I would have x minus 2 and x plus 1. So the zeros, the x-intercepts here would happen at x equals 2 and at x equals negative 1. Because that's when, right, we've got our output is 0. And so we'd have x minus 2 times x plus 1. That output is 0. Using the zero product property, that happens when x minus 2 equals 0 or x plus 1 equals 0 by the zero product property. And then we just solve each of those little equations. All right, so we factored and we use zero product property. Okay, on this one, we have it already factors. So 0, when is this all equal to 0? And that happens a bunch of places when x equals 1, negative 5, 6, and negative 3 by the zero product property. Okay, once we figured out the zeros, now we can think about what's happening around there. Okay, so we figured those out. Now, is it crossing where the graph is going, down on one side, up on the other? So the intermediate value theorem has a fancy name for a pretty straightforward idea. Basically, if the output has a different sign on either side of those zeros, then it has to cross. So we can always test points and figure out if it crossed or not, or if it just touched. Now, sometimes we don't want to always have to plug in a bunch of points because there might be a lot of zeros, like on our last example. And so one thing that can help us is this idea of what's called multiplicity. So basically, if you have something like x minus 1 quantity squared, okay, that is kind of our nice typical quadratic, but that's been slid over to the right. Okay, so this is just a touch point. It didn't cross, and that happens when that 0 has a multiplicity of 2. Okay, so what does that mean? That means that basically that factor, x minus 1, has a degree of an even degree. I'll show you some examples to kind of help you, but if we had something like y equals x minus 1 quantity cubed, then that, because this is even or odd, it's going to cross instead of just touch. So this would be our cubic graph. All right, and then one other thing is this idea of what's just the local extrema. You can't have any more than 1 minus the degree of local extrema. Okay, so let's put all this together and start acting like graphing calculators ourselves. Okay, so here we go. We're going to graph this function. Okay, so what we're trying to do is avoid just having to make this ginormous XY table and plug in a whole bunch of points. Okay, so the first thing I'm going to do is try and figure out some zeros. So I'm going to factor. So I'm going to set our polynomial equal to 0, and here I can factor out an x, maybe a negative x. So I'd get 3x squared plus x minus 1. Okay, and then zero product property tells me x equals 0. That's 1, 0, and then I'm going to use quadratic formula to find the other. So a is 3, b is 1, c is negative 1. So x equals opposite of b plus or minus square root of b squared minus 4 times a times c, so just plug in those values in, all over 2 times a. And you can just pull out your calculator, and we would get that, let's see, x equals 0.43 and negative 0.77 approximately. All right, so we found 3 zeros. And now we want to figure out our y-intercept. So you basically just now make a kind of a shortened little xy table for yourself. So x and p of x. Okay, so I'm going to do, let's see, negative 0.77. Okay, that is a x-intercept. That only happens once. Okay, so that means the multiplicity of that is 1, so that it tells me it's across. Okay, at 0, that's another x-intercept, and that is also a cross point because that only happens once. Okay, and then our other one is at 0.43, and that is also a cross point. Okay, now I think about end behavior. Okay, I have a negative leading coefficient and an odd degree. So that means that y is going to go towards, let's see, negative leading coefficient. So usually we're thinking about kind of like a y cubed type of thing, but here y is going to go to negative infinity as x goes to, right, because it's reflected, so as x goes towards infinity, and y is going to go towards positive infinity as x becomes more and more negative. All right, so that's our end behavior. So now let's figure out, we know we might have to do a few more points, but let's just at least put our points in there. Okay, so that's a cross point. I'm just going to count by ones. All right, so we have negative 0.77. That's a 0. And 4.3, that's a 0 as well. So we know it's supposed to be, as x is going towards negative infinity, y is positive. So it's coming like that, and then on this side it needs to be going down. So I have it crossing and popping back up and then crossing again. And if we wanted to get a little bit more specific about, you know, how steep those are, we could figure out a couple little points. So this one is at 0.43 and 0. This is obviously at 0, 0, and then this one is at negative 0.770. All right, let's do another one. So we're sketching the graph here, and notice that we have this factored x minus 1 is times itself, and then x plus 2 is being cubed. So if we set this equal to 0, we've got zeros at x equals 1 and negative 2. Okay, so when I go to make my XY chart, we would have at 1 we have a 0, and at negative 2 we have a 0, and at 1 we have a 0. But are those crossing or are those touching? That's the question, and the answer to that is based on the degree of those zeros. Okay, so that's the multiplicity. At negative 2 we have an output of 0, and then at 1 we have an output of 0. Okay, because we have an even degree On the 1, that means that that is a touch point. And because we have an odd degree here, that means that's a cross point. Okay, there we go. So now we need to think about the overall degree of the entire polynomial. So the degree is 5. You just add up each of those exponents. You know, here we've got x would get multiplied times itself 5 times if you FOILed all that out. So degree of 5, and we also don't have a negative, nothing negative in front of here, so that means there's the little secret positive 1. So the leading coefficient is positive. All right, and that gives us the end behavior would be y is going to be going to infinity as x goes to infinity, and y is going to negative infinity as x goes to negative infinity. Okay, so we know we're coming from down here and we're headed up at the end. And let's see, let's think about our y-intercept. That happens when we plug 0 in for our input. So that would be -1 squared, and then 0 plus 2, that's just 2 cubed. So that would give us 8. Okay, so we have a y-intercept way up here of 8, and then we're touching there. And we don't really know how steep it is. It's sometimes kind of nice to plug in a few other numbers. If you plug 2 in here, you would get 2 minus 1 squared, 2 plus 2 cubed. So that ends up being 4 cubed, which is 64. So our graph is going extremely steep. Right? We're going from 8, we go down and we touch, and then we're going to go way up because by the time we get to 2, we need to be at positive 64. And so there we've got a general shape, just in terms of when it's increasing, when it's decreasing, when the output's positive or negative.